this video, we're going to be talking about particle motion and how we can use particle motion to calculate distance and displacement. So one thing you need to remember is that displacement is s t final minus s of t initial. Now remember that s stands for position, and so st final is your position at your final time, and st initial is your position at your initial time. So to find your total displacement, you take where you ended up and subtract that from where you started. Also recall that average velocity is the change in distance divided by time. So velocity is the distance divided by time, so we can say that that is the derivative of position. And so instantaneous velocity is the derivative. So the big difference here is average velocity is the change in distance over the change in time, and instantaneous velocity is the derivative. In example 4, we're going to look at a particle that moves along a line so that its position at any time when t is greater than or equal to 0 is given by the function s of t equals t squared minus 4t plus 3, where s is measured in meters and t is in seconds. So before we move on, I actually want to look at the graph of what's going on. So this on the left represents the graph of t squared minus 4t plus 3, and then we'll deal with this thing on the right in a minute. And so we have that as we zoom out, it's only when it's greater than 0 and it goes on forever. So if I move this slider, you can see that the position is decreasing and then begins to increase. So particle motion moves along a line. It does not move along a curve like this. It moves along a line. So when I play this, you can see that it's going to go backwards and then it's going to go forwards because it's increasing. So if I start this from 0, it goes backwards, hits the bottom, and then moves forward. Again, it's following the shape of a parabola, just condensed down to one line. So for part A, we want to find the displacement of the particle during the first 2 seconds. So during the first 2 seconds. So we know that displacement is the position of t final minus the position of t initial. So our t final is 2 because it's been 2 seconds, and our initial time is 0 because it started at 0 seconds. So now we just have to find s of 2 and s of 0. And so we have that the displacement is negative 4 meters. So during the first 2 seconds, this thing has moved negative 4 meters from its starting point. For part B, we want to find the average velocity during the first 4 seconds. So we have that average velocity is equal to delta S over delta T, and delta S is going to be S of 4 minus S of 0, because that's the change in my position, divided by B minus A, or the time difference. So now all you have to do is plug that in and solve. And so we get our average velocity is 0 meters per second. And I know what you're going to ask is, how can something that's always moving have an average velocity? Well, that's because as the particle moves backwards, the velocity is negative, and as it moves forward, it's positive. And so what's going to happen in the first 4 seconds, it's going to travel an equal speed backwards and an equal speed forward, and they're going to cancel each other out. For part C, we want to determine the instantaneous velocity at t equals 4. So recall that the instantaneous velocity is given by the derivative of position. And so we have position is t squared minus 4t plus 3. So s prime of t is equal to 2t minus 4. And so I want to find the instantaneous velocity at 4. And so I get 2 times 4 minus 4, which gives me 4 meters per second. This number represents how fast that particle is moving at that exact second at t equals 4. So we're not finding the average velocity since the beginning. We are finding how fast the velocity is when t equals 4 seconds. And now I want to determine the acceleration at t equals 4. So recall that acceleration is given as the derivative of velocity. Well, I know my velocity function is 2t minus 4, so the derivative of that is just 2. So then a of t is equal to 2. So then a of 4 is equal to 2 meters per second squared. And so now on your own, I want you to try this problem and all the following steps. So a particle moves along a line so that its position at any time when t is greater than or equal to 0 is given by the function s of t is equal to t squared minus 3t plus 2, where s is measured in meters and t is measured in seconds. So I want you to determine the displacement in the first 5 seconds, the average velocity in the first 5 seconds, the instantaneous velocity when t equals 4, the acceleration of the particle when t equals 4, and then I want to know at what values of t does the particle change direction, and where is the particle when s is a minimum. Try to do E and F on your own as well, even though it wasn't in the previous example. So for part A, I want displacement, and I know displacement is delta S, which is S t final minus S t initial. And so I get this is S of 5 minus S of 0. And so we get the displacement is 10 meters. For part B, we want to find the average velocity. And we know that average velocity is given as delta S divided by delta T. And we already know delta S is 10 meters. And that was from the previous problem A. And our delta T is 5 seconds. And so we get this is 2 meters per second is our average velocity. For part C, we have S of t is equal to t squared minus 3t plus 2. And I want to find my velocity, which is given as the derivative of position. And the derivative of position is 2t minus 3. And now I want to know my velocity at 4. So I get 2 times 4 minus 3, which is going to give me 5 meters per second. For part D, we need to find the acceleration. So our velocity is 2t minus 3. And I know acceleration is the derivative of velocity. So I get 2. So A of t is equals to 2 meters per second squared. So then A of 4 is just 2 meters per second squared. And now we're going to move on to the parts of the problem that were a little bit extra. At what values of t does the particle change direction? So we want to know for what t value does the particle go from moving forward to backwards or backwards to forwards. For something to change direction, it has to come to a stop. So if something is moving backwards, it has to stop and then begin moving forward. So if something is moving backward, it has to stop to turn around to start moving forward. So the point at which the particle changes direction is when the velocity is equal to 0. So to solve this, we have our velocity function, which is 2t minus 3, and all we have to do now is set that equal to 0 and solve. So we know that our particle then changes direction when t is equal to 3/2 seconds, or 1.5 seconds. And so I want to know, where is the particle when s is a minimum? Well, s is a minimum, so the particle is at a minimum of s, which means its position is a minimum when the velocity goes from being negative to positive. And that's because it's at a minimum because it's going backwards and then turns around and goes forwards. And since this thing never turns around again, the minimum is when t is equal to 3/2 seconds. So in order to find the position, we're going to plug that time into our position formula. So s of 3/2, and then all we have to do now is solve. And so we have the position is equal to -1/4 meter.